what I want to talk about today is on privacy utility trade-offs with synthetic data under Reconstruction attacks. That's the title of my thesis. I don't have enough time to talk about the whole thing, but what I'm going to do is talk about maybe the first half of it. Okay, so imagine you're the ABS. You've just taken the census. There's actually, I think the new census is in August this year. So when you're filling out the forms, this is something to think about. But you've collected your database. You've got something which looks like this. You've got a table where you've got rows corresponding to individuals, and you've got some columns corresponding to attributes. We'll call our database X, why not? And you can partition the attributes up into some sensitive ones and some non-sensitive ones, and also some identifying information, which is what you've got on the left-hand side over here. Okay, so generally what you want to do, I'm simplifying, but what you want to do is you want to publish some information on how these non-sensitive attributes are related to these sensitive ones, both to each other and within each other. Seems easy enough. But the difficulty with this, and I guess the reason why you need to do a PhD in this, is because you need to balance these competing goals of privacy and utility. So on the one hand, you want the information that you publish to be accurate enough for someone or some researcher to learn that smoking causes cancer, but at the same time, you don't want to allow anyone to learn that any individual in the database is a smoker. So these are sort of the two competing objectives, which the goal of when you're trying to publish this information, you need to manage. I should say as well that a lot of what I'm talking about comes from this traditional statistical organization setting, such as the ABS, collecting demographic information to inform policy decisions. But a lot of it extends beyond that to modern settings. For instance, recommender algorithms trying to determine what film you want to watch, but you might not want anyone to know what films you've been watching. So a lot of the principles apply more broadly, but the specific focus that we've been working on is this traditional setting. All right, so the key research question that we've been trying to answer is, how can statistical information about a population be published while maintaining the privacy of individual records? All right, so how do you do this? The first thing that you might think of is you take your database, looks like this, and you've got this identifying information on the left over here, some names, some email addresses, unique ID numbers. You might then want to strip that off, and then you can publish the database restricted to the set of attributes consisting of the non-sensitive and the sensitive ones, and you just hide those identifying information. I should say as well that I guess this is a bit of a timestamp of when I have been developing these slides, because this is sort of severance loaded terminology. But yeah, so this is what you might want to do. You might want to publish this database like this, restricted to these attributes, but this is a bad thing to do. And this is exactly what happened in 2016, where the Australian government released a 10% sample of pharmaceutical benefit scheme, Medicare benefit scheme billing records. So this is longitudinal records. So someone gets treated for a cold, 3 weeks later they get treated for a cold, and 4 weeks later they have some antibiotics, something like that. So 10% of Australians, it's not the entire database. You only have 3 million people, and the span of records is 30 years. They published that information, trying to in a policy of open government data. And there was a group of researchers at the University of Melbourne, one I forgot to invite to this session, but it's recorded. And basically what they found is that you could uniquely identify an individual based on a very rudimentary combination of attribute values. So what they did is they looked at the mother's birth year, they looked at the child's birth year, and a second child's birth year, and provided that that mother gave birth late in life or early in life was enough to uniquely isolate an individual in that database. Once you have isolated an individual, you can then go and look up on another source of information, Wikipedia, another database. You can then link that individual to someone's name. So, I mean, mother's birth year, children's birth year, other children's birth year is enough to isolate an individual. You can then go and look up more and more information about that person to make sure you're sure that you've got the right person. The example that they gave was Kathy Freeman. They just looked at Kathy Freeman's name on Wikipedia. And then you can go and have a look at your billing records and determine that they had treatment for some rare disease or something like that, which reveals the privacy. Roughly, this is what it looks like in a picture. Here's your database X. You restrict your database X to be these attributes on the right-hand side. I've called the non-sensitive information quasi-identifiers here. And then you've got some sensitive information. You then go and take your other database, Wikipedia, for example, and you link these two through this set of publicly known attributes, and you get a complete picture of what the original database looks like. After they did this, these group of researchers, George Brandis, who was the Attorney General at the time, is a barrister, decided to fix this problem by criminalizing any attempts to do any sort of re-identification. As they pointed out, this doesn't really do anything to stop anyone trying to do this sort of re-identification process. All it does is just damage the freedoms of the researchers working in this area. So clearly we can't rely on a legal solution. We need a mathematical solution which addresses the actual fundamentals of the problem. Okay, so if we can't publish the entire database, we can publish queries. We're going to focus on counting queries, Q of X. So Q is just going to be some function of X. A query is the form, how many women under the age of 20 in postcode 3000 are smokers. It counts the number of individuals that those attributes you predicate on are in that demographic region. So this is the focus of what we're interested in. There's other types of queries, but let's just think about counting queries. And so the issue is that you can't just publish every answer to every possible query. The set of queries, there's a bijection between the full set of queries and a unique database. It's basically equivalent if you publish all of these queries accurately to just publishing the database, which we saw in the example that I just gave is a bad thing to do. So we need to do something a little bit more. I'll also give you an example of justifying this statement, how it's equivalent. So what can you do if you can't publish all the queries? You can publish less of them. This is known as suppression. Basically, rather than publishing a count of a query, Q of X, you publish a star or a symbol that indicates that you've suppressed that value, or you could just publish a 0. That's an explicit way of suppressing the amount of information that you publish. An implicit way of doing it is that you just aggregate or coarsen some variables. You don't allow someone to ask how many smokers aged 55 live in Balaclava. You only allow people to ask queries, how many people aged between 50 and 60 live in Balaclava. It's another way of suppressing the total amount of information that you publish. The other thing that you can do is you still publish answers to queries, but you lie. You give, rather than publishing the true answer, say there's 100 people that live in 100 smokers in Balaclava, you say there's 102. But what you do is you give some error bounds on that. You say, well, the true answer is plus or minus 5. So I'm saying it's 102, but really it's going to be 102 plus or minus 5. That's a way to manage the privacy concerns associated with publishing accurate answers. And I should say that this method here, this perturbation approach, is the method that we're focusing on. And I refer to the perturbed values of queries with a hat, as opposed to just the true values Q of X. I should say as well that these two approaches are often used in conjunction with one another. All right, so Having set this up, what are the different ways that we can perturb the queries? Well, there's this standard approach, which we call the output noise mechanism. Basically, you ask a query, you add random noise to it, and then you publish that answer. And every query that gets asked, you do that independently. So you add a different realization of the noise independently to each query, and then you publish the result. This is actually what the ABS does with Table Builder, and Table Builder is actually the motivation for the model, which I will present. But yeah, this is one approach to perturbing the values. The other way is that you can use this synthetic data mechanism, which basically means you get your true database, you perturb that. So rather than adding noise at the output query level, you add it to the database level, which is also called the input level. And then you answer all queries using that synthetic database. So to give you an example of what these look like, here's your database. I've just got two binary attributes, gender and smoking status. And if we go ahead and tabulate that data, we get a table which looks like this. It's just counting the occurrence of those attributes that we're predicating on. So there's how many male smokers are there. Just have a look at the table and you count that up. You can see this as being 9 individual queries related through some set of linear constraints. If you go ahead and apply the output noise mechanism approach to that, and you assume that the amount of noise that you add is going to be plus or minus 1, what you can do is you could add noise independently to each cell using the uniform distribution over the set -1, 0, 1, and you might get something which looks like this. You get some plus ones, you get some minus ones, you get some zeros, and you add them on to your true counts, and this is the perturbed table that you then publish. Okay, so some observations about this is, firstly, it's easy to satisfy that bounded noise constraint. If you want to make sure that the perturbations lie within plus or minus 1 of the true value, this approach does it immediately. But what happens is you lose this consistency property. So now the number of male smokers plus the number of male non-smokers doesn't equal to the total number of men in the database. You might think that that's outrageous, but this is exactly what the ABS do when they publish counts. And I guess one of the first meetings that we had when we learned about this from the ABS is this bad? Does it weaken the privacy guarantees? Do these inconsistencies leave something to be exploited? So that was, I guess, the motivation for investigating this. The other way we could add noise is with this synthetic data approach. So you take your true database X, you add some noise to it, Z. I'm not really explaining how this occurs, but you can generate a synthetic database X hat, and you're perturbing the underlying database. So specifically, I've made one of these men pick up smoking and one of these women have decided to quit smoking. You go ahead and you tabulate the synthetic database relative to the true one, and the result is that you're effectively applying perturbations which look like this to the original table. You can see that there's one more male smoker and one less male non-smoker. And this is the table that you will then publish. It respects these linear constraints. So now the number of male smokers plus the number of male non-smokers does equal to the total number of individuals. But it's a lot trickier to satisfy that bounded noise constraint of plus or minus 1 perturbation. For example, if I made another female pick up smoking, or I made another male quit smoking, something like that, suddenly the errors on the perturbed table blow out, and I have no guarantee of the trust that I'm providing to individuals using this data. Researchers might not know where to build the smoking rehabilitation clinic if you add too much noise. All right, so reframing our research question before, now that I've presented two methods, which one has better privacy utility trade-offs? We've got two things, privacy and utility. How we can measure both of them at the same time or give a sense of which one has better trade-offs is we can fix one and measure the change in the other variable. So specifically, if we fix utility and measure the privacy guarantees, this is the approach that we'll take. So how we fix utility is we enforce this bounded noise constraint. So query answers must be accurate to at most R error. So the plus or minus one before, now R, I can generalize it. And having fixed that utility constraint, we can measure privacy with some reconstruction attacks. Basically, what can you reconstruct about the underlying database given the observed outputs? I'll give you an example of what that looks like, but I should say that no one's done a direct comparison between these two methods before under this framework, which is relatively natural. And I'll explain why I don't think anyone's done one of those before, but this is the setup. So here's a very simple example of what a reconstruction attack is. Say you publish the outputs, you say that there's going to be 3 people in the population, there's 1 smoker, the average age of the smokers is 45 years old, the average age of the non-smokers is 30, and the number of people aged 25 is 1. What's the underlying database? Is there a unique database which relates to this set of aggregate statistics? In this case, there is, but in general, that question is hard to answer. So if we, I guess this is a warm-up example, if we go through and actually think about what the database is, it's not hard to see that the number of smokers, if there's 1 and the average age of the smokers is 45, there will be 1 smoker aged 45 years. There will be 2 people that are non-smokers in the database if there's a total of 3. And we know that one of them is 25 and the average age of the 2 of them is 30. So the other one will be 35. And this gives us the database here. This is really simple, the example that I've given you. But this also works when you publish perturbed values with bounds on the noise as well. It complicates it a lot, so I didn't include that, but the same ideas apply. All right, so this is basically the setup of the problem. I'll actually show you and present the model that we've been using to answer this question. And to motivate the model, I will explain how we've abstracted all these real-world considerations down into literally the simplest way that you could probably model some information. What you do is you take your database, you assume that all of these non-sensitive attributes are known and uniquely identifying to the attacker or the person that's trying to infer what an individual sensitive attribute is. You assume that the sensitive bit is unknown. And if all of these known and uniquely identifying attributes are publicly available, then you can replace all of them with a unique ID number. This fact that they're known and uniquely identifying is not unreasonable considering that example that I gave at the start with the pharmaceutical benefit scheme billing records. So once you have your, you can think about this as going to be some unordered set with a unique ID and smoking status. You can just fix a row order, make it an ordered set. It becomes this, and then you can encode these attribute values. In this case, they're binary, so we can put a 1 if they're a smoker, and we can put a 0 if they're not. And now we've taken our complicated real-world database, and it's a binary vector. So this is, for people that don't know, I guess, how applied maths works, this is a very standard thing to do, is to simplify the problem down literally as much as you can and see what you can learn. Okay, so this is from this point on, it gets a little bit mathsier. So the database is going to be a random variable. We'll call that X. The realizations of this random variable are going to be denoted by the lowercase. It'll be a binary vector of length n, where the entries can take value 0 or 1. 1 indicates that the individual is a smoker. 0 indicates they're not. Queries from before were how many smokers do I have in some suburb? Now they become how many smokers do I have in a subset? And you can write down what this subset is as also a binary vector of length n, and you specify the individuals that you want in that subset by putting a 1 in the entry. So if I want to ask how many smokers do I have in this half of the room, there's a way of writing down a vector which corresponds to all 1s in all those entries and 0s in all the other ones. We can compute the true answer to this query. I've denoted the query by a subscript b referring to the subset b. You can take the dot product of those two vectors, and that gives you the true count. And more efficiently, you can write this query matrix, capital B, which will be composed of individual rows of subsets B. So this query matrix is going to be an m by n matrix, where m is going to be at most 2 to the n by n, because that's the number of allowable subsets that you have of a binary vector of length n. And yeah, so what we want to do when we apply our perturbations is we want to respect the original sort of motivation, this table builder setting. Basically, we want the query answers to be non-negative. How many smokers do we have in this half of the room? -2. We want to stop that from happening. So we restrict them to be non-negative. We want them to be integer valued so that they respect counts. I've got an asterisk here, which is because some other systems around the world allow fractional outputs to be published. How many smokers do I have in Turak? 52.5. That's allowed. Whether that's a good thing or not, I'm not sure, but that's the asterisk. And then the other constraint that we're imposing is this bounded noise constraint. So I've written down this constraint as the L infinity norm of the difference between the perturbed value and the true value, implicitly assuming that these are going to be vector valued queries, and the L infinity norm just takes the maximum entry across all of those entries of the vector, and it makes sure that they're less than R. Okay, so these are my 3 constraints that I want the outputs to have. With the output noise mechanism approach, this is the description of the output noise mechanism. As a function, it takes in the true database X, and it takes in a random variable Y. And it works by you compute the true answers to the queries on the database X, and then the output will be something in m dimensions, and then you add an m-dimensional random vector Y to those outputs, and which looks something like this. And what I'm going to do is I'm going to assume that the random variables X and Y will be independent from each other. And I'm also going to assume that the entries of the vector Y are going to be independent and identically distributed. So how do we enforce these constraints? I've also wrapped this expression with a max operator, basically truncating values at 0 or below 0 to be 0. This is because the random variables X and Y are going to be independent. And these other constraints, that they're integer valued and going to have bounded noise, you just choose a distribution with an appropriate support. So the -1, 0, 1 example that I gave at the start does this. With this synthetic data mechanism, it becomes a little bit more complicated. So I've drawn a picture. We take our random variable X, we add some noise to it Z. So Z is going to be different to Y. Z is going to be of dimension N, which is the dimension of the database. And you add X to Z, and then, which gives you this synthetic database X hat, and then you publish the queries on this synthetic database as the true values, as the perturbed values. how we enforce that the values are going to be non-negative and integer valued. The outputs will be non-negative and integer valued. You need to expand the state space. So calligraphic X here is going to be the space of the feasible databases. Now we need to allow our synthetic databases to take values in a larger space here, and specifically that means that the entries of the synthetic database are no longer binary, they can take integer values. And that's just to ensure that the outputs look the same between these two mechanisms. The bounded noise constraint is a little bit trickier. We can't just choose any database in this space of feasible synthetic databases. We need to choose a restricted set. That's this blue ball here. So this is what we call the query bounded R neighborhood. So this is your true database X. You can only choose databases which are close to X, effectively. If you choose a database which is too far away from the original one, then you're going to add too much noise to the published outputs. I've written down this query bounded R neighborhood as you just take the L infinity norm of the transformed vector by this query matrix, which just comes out as Z is going to be the error, and you scale up the amount of error in query space, and you just make sure that the maximum amount is going to be less than some value R. It seems easy enough when you draw a picture, but actually trying to select a synthetic database in this blue region becomes very complicated. Rejection sampling doesn't work. You choose an appropriate proposal distribution, even with moderate sized databases. The proposal distribution grows exponentially, whereas this space, the blue ball, grows polynomially, so it doesn't work. You need to come up with some better ways of doing it. You need to think a little bit harder about the problem. And when I said before that no one's done this comparison before is because of exactly this region. It becomes very hard to do a direct comparison between these two methods, and you need to use, even when you simplify the model down to be as simple as possible, you need to use a different algorithm, which is what we did. So this is the Metropolis-Hastings algorithm. The idea is that you start at the true database, you do a random walk around the space of synthetic databases, and you're basically checking if you're inside the ball or not at each step. So is an animated version of that. Suppose that you're at some synthetic database. Here at iteration K of the algorithm, you've started off at the true one, you uniformly select its neighbors at random, and let's say you propose to move to this database. Rain.
Get moving now.
Yeah, seriously. God. All right, so you look at one of its neighbors, you check if it's inside the ball. If it is, you move there, and kind of you just rinse and repeat. You look at this new database. If this is outside the ball, as it is here, then you choose to reject that proposal and you stay where you were at each point in time. And you run this. You let this algorithm do a random walk around the state space for an infinite amount of time, and you'll converge to the uniform distribution over the set of this query-bounded R neighborhood, giving you a way to sample a synthetic database and actually do some experiments between these two approaches. One issue is that checking whether you're inside the ball or not requires potentially an exponential number of steps. So this vector is, I said, you can have at most 2 to the n queries. So checking 2 to the n entries, making sure that they're less than R in absolute value at each point in time is going to take a very long time. So you need to think of a better way of doing this. So rather than measuring the magnitude of the transform vector in query space, high dimensional query space, you want a way to measure the magnitude of the vector or the error that you add in database space, which is a lot lower dimensional. And that's what this notation here is, which is called the query norm. So it's a norm that we came up with as far as I asked ChatGPT, and it seems like it doesn't exist anywhere else. This is what it looks like. Basically, that's the definition of the norm at the top. You take your vector, you sum up all the positive entries of the vector, that gives you V plus. You look at all the negative entries of the vector, that gives you V minus. You take the negative of that and you compare which one's larger. So if you have a look at, if you plot the unit circle is all the points in the plane which are a distance of 1 away from the origin. In this query norm, that's what the unit circle looks like. It looks like a diamond. In 3 dimensions, you can plot the unit sphere. It looks like this 14-sided die. So I guess the reason why I'm plotting this is because it maybe indicates how the geometry changes under this measurement as opposed to standard ways of measuring distance. All right, so we're getting there. We've nearly at the point where I can show you the results. So the setup is you have an attacker. They ask some queries. They know the query matrix B. They observe the noisy outputs Q hat. Their goal is to find a candidate database in the set of feasible databases consistent with the published answers. Given that they have a candidate database, which they think is the right one, you can compare that to the true one. You can see how many entries agree and allows you to transform that into a score. An accuracy of 1 indicates that you've got every single person's smoking status correct. 0 indicates you've got them all wrong. You can get an average and do this many, many times, and you can interpret the average reconstruction accuracy as the probability that you're going to get any particular individual smoking status correct. You don't just need to find one candidate database. If you have an integer linear program, you can enumerate the set of feasible databases using Garobi, which we've done. So these are the attacks. There's some linear programs, or you can reformulate them as integer linear programs. That's these first 2 attacks. The difference is you add an objective function onto the second one. I had a question before I came in here. Who's Alison Harcourt? That's her on the wall. The reason why she's famous is, well, one of the reasons why she's famous is she came up with algorithms to actually solve these formulations of the problem. She's 96 or 7 or something like that. So thanks to her, we can do this. The other attack is we use this pseudo-inverse method. Basically, it's you take the generalized inverse of a matrix and it solves some least squares optimization problem to give you a candidate database. Just to make sure that I'm not cheating too much with my comparison, what I'm doing is I'm randomly selecting a query uniformly at random, and I'm making a histogram of the error that query would give. And as you can see, the amount of error, which is on the horizontal here, is roughly the same. So the synthetic data mechanism is black. The colored ones are the bad approach, or the one that the ABS uses, or that we're comparing against. And you can see that they're relatively comparable when I implement them with the triangular noise, normal noise, or uniform noise. If we actually plot these reconstruction attacks, we get something which looks like this. I'm asking an increasing series of questions on the horizontal axis. This is number of queries here. You ask more and more and more queries, and you plot the average reconstruction accuracy, the colored lines, that independent noise approach, the output noise mechanism. The reconstruction accuracy quickly converges to 1. That means that you can determine exactly what the underlying database is, revealing the privacy of the individuals, despite thinking that the protection methods that you've used are good enough. In comparison, you've got this black line, which is the method that we're proposing, the synthetic data approach. And as you can see, the average reconstruction accuracy is a lot lower. And this is, I guess this is quite insightful because no one's done a comparison like this before where you can really quantify the difference that these two methods have. You can increase the size of the database. So before it was size 12 with a noise bound of 3. Now I've got a database of size 50 with a noise bound of 7. You can't do exponential queries. So what I've done is I've done polynomial number of queries and the same things apply. And because the same things apply as you scale it up, we would expect the same things to occur in real world settings as well. Why does this occur? One way is that you get this feasible set reduction. So if you think about the allowable databases or the set of feasible databases consistent with those published outputs, when we have those inconsistencies, which I talked about at the start, they constrain the set of feasible databases to be a strictly smaller set, and that provides information to the attacker. An example of what this looks like is if I ask the query, how many men do I have in my database? How many women do I have in my database? What's the total number of people? Suppose that the true counts will be 5, 5, 10. If you perturb the value, so you get a 4, 5, and 11, there's 3 feasible true counts that perturbed values could take. If the observed output by the individual is 4, 4, 11, so you've added -1, -1, and +1, there's only one candidate, there's only one feasible configuration of the noise consistent with that plus or -1 output. So you're effectively removing the perturbations if someone observes this. Whereas if you have this consistent property, which is what you always get when you use that synthetic data approach, you have 6 possible outputs, which creates more uncertainty about what the true database is. So that's one way that these attacks work. If you don't have the bounded noise constraint, or you are using unbounded noise distributions, or even if you use distributions supported on the set of real numbers as opposed to integers, you can do this thing where you use noise averaging. So basically, if you're trying to figure out what the total number of smokers is, you could ask how many male smokers do I have, ask how many female smokers I have, combine those two answers to get a noisy estimate of the total number of smokers. Another way that you could do this is you could ask how many young smokers do I have and how many old smokers do I have, combine those, you get another noisy estimate. You kind of keep doing this and you can apply some law of large numbers and get an idea of what the true value is, provided that the distribution of the noise will be have mean 0. This is a very simple example of how this noise averaging can occur. The actual attacks do this sort of thing where they consider all linear relationships at the same time to get an idea of what the minimum noise is. So that pseudo inverse method that I talked about before, it does a least squares kind of approximation, and this is what it looks like. So this is that pseudo inverse attack, and so this is not using any of those feasible set reduction. It's just doing noise averaging, and you can see it performs very well. So I guess one of the observations that we have is that even if the attacker can figure out what the synthetic database is, that's the perturbed one, there are still many possible databases that synthetic one could have come from. So if this is our true database here, X, say we output this one over here inside the blue region, it lives in the space of feasible synthetic databases. what the attacker will then do is it'll form a ball around that synthetic database based on the information that it's asked. That's why I've put the query matrix as a function, as an argument to this function. And then you intersect that green region with the space of feasible databases, which gives you the red region, and that is the set of candidate databases that your synthetic one could have come from. So when this set is large, you get good privacy. It can happen that you'll have something like this on the left where that set's large. The attacker can't figure out very much. Or you could get a situation like this where the intersection is small, meaning that the attacker could learn a fair bit about what the synthetic database is. But this, I guess, is an artifact of using these bounded sets, which I've drawn as circles here. Another thing that you could do instead of using this bounded noise constraint is you could use a different sampling distribution like this, where you sample a synthetic database with probability proportional to, or inversely proportional to the distance between the true database and the output one. And when you do that, you need to analyze this approach with this approach called differential privacy, which is the second half of the thesis. So I'll stop there.